Let's look at two examples. First, let's burn some methane. If we go look up the S values for these chemicals, we'll find that methane is 186.1. These are all in joules per mole Kelvin. So how distributed the energy per temp for a mole of these? It's 205.0 for oxygen, it's 213.7 for carbon dioxide, and it is 69.9 for water. So we can find just the change in entropy for this reaction. So this is the change in entropy for the system. Well, it's going to be the sum of the products minus the sum of the reactants. 213.7 plus 2 times 69.9 minus 186.1 plus 2 times 205.0 for the water. Bring that together, we'll find that the S value for this reaction, the change in entropy, is minus 242.6. For each mole of this reaction formula, 242.6 joules per Kelvin is lost. Well, a negative entropy is disfavored. Entropy should always increase. But that's for the universe. A reaction itself can decrease as long as the surroundings increase. Well, if we think for a minute, why did this go negative? Well, I had 3 moles of gas particles and I end up with only 1 mole of gas. I have 2 moles of water. Liquids are not nearly as entropic as gases. They don't have as many freedom of motions. They have to stay near the other molecules to be bound to them, where a gas can spread out in many distances and directions. So reducing the number of gas moles almost always reduces your entropy. How then does this reaction occur? Because methane quite readily burns. Light your stove if you got a gas range, and it will just nicely burn on its own. You only have to spark it to get it going. For this, we need to look at the delta S of the surroundings. When you convert these molecules, they give off a great deal of heat. There's 890 kilojoules that is emitted, as the delta H for this reaction is negative 890 kilojoules. 890 kilojoules is given away to whatever happens to be around to absorb it, to the rest of the universe, its surroundings of this reaction. Well, for that we need to calculate delta H normally. That would be that the delta H of your reaction is going to equal the sum of the delta H of formations of your products minus the sum of the delta H of formation of your reactants. So same way we just solve the delta H of reaction from its standard values, we can solve delta H formation from it. Gave it here, it's 890, but if we wanted the values, methane is negative 74.87. These are in kilojoules per mole for the enthalpy. Oxygen, being the elemental form, is 0. Carbon dioxide is minus 393.5, and water minus 285.8. Run all those together. Like I said, the delta H for this reaction is going to be found to be minus 890 kilojoules. Well, the delta S of our surroundings was equal to the negative delta H of reaction divided by the temp. Turn this into joules. Negative and negative will be a positive. So negative of negative 890 kilojoules will be positive 890. And that'll be 890,000 joules over the standard state temp of 298 Kelvin. This comes out at 2,986.6 joules per Kelvin, and since we are doing a mole of the balanced reaction, the mole actually shows up in here as well. It's occasionally an odd part. It looks like it calculates out. But technically, while this is the amount for the reaction shown, we are going to use 1 mole of that reaction. Comparing this with our delta S of reaction, our delta S of the universe is going to be negative 242.6 joules per mole Kelvin plus 2,986.6 joules per mole Kelvin. As a result, the actual change in the total universe's entropy is 2,743.98 joules per mole Kelvin. Well, the molecules of methane and oxygen being reworked to form CO2 and water were less entropic. The energy it poured into the surrounding environment, causing the local environment to increase its microstates by having more energy to spread out, resulted in a greater change in total by spreading that energy out through the rest of the surroundings, and therefore the universe overall ended up with an increase in entropy. Let's try looking at one where we have a chemical change. H2O liquid going to H2O gas. Let's understand why it's favorable or disfavorable to boil. Let's look at 95 degrees Celsius versus 105 degrees Celsius. The delta S of the universe is going to equal the delta S of our system plus the delta S of our surroundings. So what's our system in this case? Well, standard S value, standard change in enthalpies of formation here for the water, liquid and water gas, 69.9 joules per mole Kelvin for liquid water, and 188.7 joules per mole Kelvin for gaseous water. Gaseous water inherently has more entropy because it's a gas instead of a liquid. It has more freedoms of motions, and we can see that in its values here. The delta H of formations for the two is minus 285.8 kilojoules per mole for our delta H formation for the liquid, and minus 241.8 for our gas. Well, the delta S of our system then is going to equal the sum of the products minus the sum of the reactants. We only have one of each. So 188.7 minus 69.9 for 118.8. There's a net increase in entropy as you go from liquid water to gaseous water. So our system is indeed increasing. Our delta H of reaction, negative 241.8 minus negative 285.8. That's going to be 44 kilojoules per mole of this reaction. So the entropy is favorable. However, the enthalpy, we have to put a bunch of energy in. This isn't going to happen unless some outside source provides some energy. Well, let's heat it up to these temps and look at what happens to the S of the surroundings. Now, this does make an assumption. The values we are using are from the standard states, which is at 25 Celsius. There is some variability as you change your temp, but we'll make the assumption that our standard state values are close when we're at these elevated temperatures. So we're going to use the values we have available to us. Well, the delta S of the surroundings, remember, is the negative delta H of reaction over the temp. So let's look at this at 95 degrees versus 105 degrees. 44,000 and negative in front, so our positive value of the negative in front becomes negative. Joules per mole divided by the temperature. 95 Celsius is 368 Kelvin, which will give us negative 119.6 joules per mole Kelvin. At 105 degrees, however, well, negative of our positive delta H, so negative 44,000 joules per mole over 378 Kelvin is going to be negative 116.4 joules per mole Kelvin. The change in entropy of our surrounding is actually dependent on the temperature at which this is occurring. If you already have more energy available, adding a certain amount of energy will only increase your available microstates by so much. At a different temperature, the amount of energy already available will be larger or lesser, and adding the same amount will have a bigger proportionate or smaller proportionate effect. Effectively, at colder temperatures, adding a certain amount of energy will have a greater change in the number of microstates than at hotter temperatures. Just because at hotter temperatures there was already so much energy, you're not changing the total to distribute by as much. And we see that in our values here. The colder temp had a higher change than the higher temp did. Plug both these in for the delta S of the universe at 95 versus 105. Well, the S value for our system was the same. It was 118.8. However, the delta S of the surroundings was different. Plus negative 109.6 versus plus negative 116.4. This gives us negative 0.8 joules per mole Kelvin versus positive 2.4 joules per mole Kelvin. Due to the entropy change in the surrounding being dependent on the temperature, at certain temperatures, the S value change for the universe would be negative. But as we continue to heat up, because that reduces the loss in entropy to the surroundings, the net effect is then we can create more total entropy by turning our liquid into a gas. The entropy for the universe becomes favorable at higher temperatures for our liquid to boil away. Why do phase changes occur? Why does water switch between liquid and gas, but only around 100 degrees? Because it is disfavored for it to turn into a gas at lower temperatures in the universe. The entropy would go down, but it is favorable to turn it into a gas at higher temperatures as the total entropy of the universe will be increased. Takeaways here, the relations, three relations we need to follow. The delta S of my reaction, or the system, is equal to the sum of the standard state S values of my products minus the sum of the standard state entropy values for my reactants. The S value for my surroundings is equal to the negative delta H of the reaction divided by the temp at which it is being maintained. And the S value for the universe is equal to the S of your system plus the S of your surroundings. These three relations allow us to calculate out the entropy for various chemical changes and chemical reactions.